Hello, Mr. Jones again. This is the second half of the AP Chemistry notes for pages 1 through 4. Now, in part 1, we had ended by doing this problem here, solving for the excess hydrogen. So now we are here. So, percent yield. It's how much you get when you do a reaction versus how much you were supposed to get, the theoretical amount. Now, you can see I wrote in my notes, you typically get less than 100%. It's pretty rare that you can get 100% of something. Things happen, cause you to not get as much as you're supposed to. Couple of reasons are equilibrium. Maybe the reaction reaches a state of equilibrium and doesn't go all the way. Another reason is just entropy and chaos. Even if you have a reaction that prefers to go forward, not every molecule runs into the other molecule that it needs to. Sometimes molecules decide to do a different reaction, and so for the most part, you never get 100%. There are some weird cases where you might get 100%, but that's a unique situation. When you do the calculation, you take the amount that you actually got, like doing a lab, you divide by what you were supposed to get by doing the math and the stoichiometry, times 100, of course, and that will be the percent yield of that product. Now, I made a note here to be careful. This is different than percent error. Percent error is an analysis of how accurate you are. Now, why people get confused between these two things is because you do both of them or one of them at the end of a lab. Percents, and you might do one of these at the end of a lab, leads to some confusion, but they are not the same thing. They're sort of related, but that's it. We're not going to do percent error today. So looking at an example, take this reaction here, C6H6, which by the way is called benzene. This is a molecule you should just be familiar with. It's an organic molecule. This is an organic reaction, so it might look a little weird to you. And you'll get more comfortable with these because I'll sprinkle these throughout our lessons as we move through the year. And you'll get more used to it. But I do want to talk about benzene real quick. It's kind of a special molecule, which looks like this. Three double bonds that are resonating, and you'd have a hydrogen sticking off of each of these carbons. I'm not going to bother drawing the hydrogens, but there would be there'd be 6 hydrogens going around these outer edges, 6 carbons, 3 double bonds that kind of resonate around the middle here. You can kind of imagine the 3 double bonds here, here, and here, and blur the whole thing together, and that's more accurate. And it's just an important starting point for a lot of organic molecules, some of which are in your body, some of which are in food, medicine, and nature, and so on. So it's something to be aware of. All right, back to the reaction. Benzene reacts with chlorine, makes this stuff, don't worry about what it is, and HCl gas. When 36.8 grams of benzene react with excess chlorine. Okay, what does that mean? Right, excess means there's a whole lot of chlorine. You don't need to worry about it. This must be the limiting reactant. You often will see this phrase with combustion reactions. You'll see a fuel plus oxygen, and the question will talk about excess oxygen because it's burning in the atmosphere. And you get whatever products are appropriate in that case. Anyway, The actual yield of this product, C6H5Cl, is 38.8 grams. What's the percent yield? What we need to know first is this is what got. We need to know how much were they supposed to get in a perfect universe. So it's a basic stoichiometry problem. Take your limiting reactant, 36.8 of benzene, turn it to moles. Use stoichiometry to go from moles of benzene to moles of product. This one here, and this reaction just happens to be a 1-to-1. And then take the product and go from moles to grams. And you get 53.2 grams of C6H5Cl. Now what that means is that this is what you were supposed to get, and the problem said what they actually got. So you take what they actually got, 38.8, divide by what you were supposed to get, times 100, you get 72.9% yield. And again, box your answer, sig figs, say percent, say yield. You could even be more specific. You could say 72.9% yield C6H5Cl. Something like that would be even better. Okay. Next, this is mainly a review. You should have done this before. I keep doing that. Called simplest or empirical formula. I like the word empirical, but a lot of people use simplest. What you're doing here is you're comparing the amount of different elements to find their lowest ratio. Now, this lowest ratio is not necessarily the correct molecule. It's not necessarily the molecule that exists in the world. It's just the lowest ratio. So, if the problem has given you grams, turn those to moles. When you do this, do not use the molar mass of diatomics. You don't know what the molar mass is yet of the molecule. You just know the molar mass of each individual element. So don't do diatomics here. This is the one and only time to ignore the whole diatomic idea. Then you're going to compare the moles of each atom to every other atom. And I'll explain this not rounding in this problem. So this problem saved us the gram to mole conversion. It just gave us moles, moles, and moles. So we didn't have to bother with that. So I've listed my elements here, carbon, hydrogen, oxygen. I've copied their moles. And you always divide by whoever the lowest is. What that will do is it will force the lowest to become an automatic 1, and everybody else will then be some higher ratio. Carbon works out to be a 2. Oxygen works out to be a 1 decimal repeating 6. Now in this case, we need to keep this ratio, but we can't with these numbers here. If I were to write the formula right now, what I would write would look pretty weird. It would look like this. It would be C2H O 1.6666 and so on, repeating. You can't have 1 decimal repeating 6 of an oxygen atom. So this does not make sense. Don't do that. We need to keep this ratio, but get this to be a whole number. Well, this is the same or 5/3, and the way to make that a whole number is to multiply by 3. But if you multiply this by 3, you have to multiply everybody by 3. So you multiply everybody by 3. The 2 becomes a 6, a 3, and this, it's hard to see here, but 5/3 times 3, of course, is 5. And now we have our empirical formula, C6H3O5. Moving on to the, actually, before we move on, let me talk about some common scenarios you see here. You now have seen the repeating 6. Repeating 3 is the same. So 0.33333. You're going to triple it. Another common one is 0.25. You multiply by 4. 0.5, you'll double. There's a few more exotic ones, and we'll deal with those when they pop up in the future. Moving on. The molecular formula is the actual real molecule. This is the thing that you can put in a beaker or use in a reaction. This is what actually exists. And the real formula has to be sum of the simplest. It can either be the simplest, the same thing, or double or triple, and so on. So in this example, the simplest formula was determined to be HO. That means it's a 1-to-1 ratio. Let me get back in there. I don't want that. Okay. And we found that the mass was 34.02. What's the molecular formula? Well, what you need to do is you need to see how many of these by mass fit into that. So the molar mass of HO is 17.01 if you add up a hydrogen and an oxygen. And you don't really need to do the math to see this, but sometimes it's not so obvious. 34.02, which I got from here, divided by 17.01, it's 2. That means the real molecule is 2 times bigger than HO. But you have to show it in this 1-to-1 ratio. And this is how you do it, H2O2. Don't do this, and don't do this. These are not the same thing. These are both saying 2 HO in some other scenario. So this is bad, and this is. Now, while we're on this, this is another thing you should be aware of. This is hydrogen peroxide, which you probably have. Most people have a bottle in the bathroom. It's in the small plastic brown container. You put it on cuts to sanitize them and such. Another note here is the difference between molar mass and molecular mass. Molar mass is what it says. It's the mass of a mole, which is why its unit is mass per mole. And that's why we use it to convert between mass and moles. Molecular mass is the mass of one molecule of molecules. So 6.022 times 10 to the 23rd of them. This is a single molecule. And so notice it doesn't have units. Or if you want to be particularly savvy, you can say AMU for atomic mass units. But we'll get into that more in the future. Moving to the next page, our last page. Just got a little bit messed up here. Let me grab this one. That's better. I'll move that down. Okay. This is something we're going to need for our first lab. Not necessarily related to what I've talked about before. And it's called Beer's Law or the Beer-Lambert Law. Most people just say Beer's Law for short. It has nothing to do with the beverage. These are people's names. And it has to do with a concept called spectroscopy. And the way it works is you take a sample of some chemical. Let's say we take a test tube. And in that, we put some colored chemical. We'll do red since that's here. I've got a bunch of red chemical in here. Then what you do is you shine light of all colors or a specific color through it. Not all the light passes through and get less light. And with the right equipment, you can measure what was the amount of light before and what was the amount of light after. And that's relative to how concentrated this is. The higher the concentration, the more red it would be to our eyes, and the less light would pass through. Now, there are some details as to what color you would want to use over here and how it all works, which we're going to explore in our first lab, which will come up really soon, actually. A couple other small things. This equation, A equals EBC. I want to go through the variables. A is the absorbance. That's how much light gets absorbed. So it's how much light did not pass through. Think of it as being stuck in here. E is to be a capital E. It's supposed to be a Greek lowercase epsilon, which looks, it's a little bit curvier like that. So you might see it look like that. That is a constant for the particular chemical. It mentions it here, the molar absorptivity, and it has to do with just how much this thing absorbs that particular color of light. B is called the path length, and that is how wide your test tube is. In other words, how much distance does the light have to cover? So in our particular case, B would be this distance from here to here. Make that look better. Okay, like that. C is the concentration, typically in molarity, and we'll see that in the lab. I'm mainly just introducing this right now so you have a little bit of background before we get to the lab, and we'll cover that in detail.